dear students of class 12. Today we will be continuing with chapter 2, that is solution, and today's topic is depression in freezing point. So depression in freezing point is one of the colligative property. Before this topic we had discussed two colligative properties, elevation in boiling point and relative lowering of vapor pressure. So you know what is colligative property? Colligative property are those properties which depend upon the number of moles, okay, number of moles of the solid or the particles. So whenever we have discussed in our previous video that whenever a non-volatile solid is added to a solvent, then its vapor pressure decreases, and as a consequence of that we had elevation in boiling point and there was relative lowering of vapor pressure. So as we know what? We know that whenever a non-volatile solid is added, then this results in, whenever it is added to a solvent, then this results in lowering of vapor pressure. This results in lowering of vapor pressure. Now, so to understand this depression in freezing point, let's do it graphically. So let's draw a graph where on the y-axis you have vapor pressure. As you go up, vapor pressure increases, and on the x-axis, as you go towards the more right hand side, then the temperature increases. So whenever a non-volatile solid is added to a solvent, then this results in lowering of vapor pressure. So from this we know that the vapor pressure temperature curve for the pure solvent, pure solvent will be higher than that of the solution. So suppose this is the vapor pressure curve for, say, the pure liquid. This is the curve for pure liquid. Now you know what is the freezing point? Freezing point is a point, or is the temperature at which this solid and the liquid, they exist in equilibrium, or you can say it is a temperature at which the vapor pressure of the liquid and the solid will be same. So now as I told you, this curve, so this is point A, this is B. Now at this point, till this point, from A to B, this particular pure liquid solvent will be staying in liquid state. So if we further decrease the temperature, then this will exist in what? It will be existing in solid state. So this is the point at which the vapor pressure of the solid, this curve from B to C is the vapor pressure temperature curve for solid, pure solid, okay, and from B to A, this side, it is the vapor pressure temperature curve for pure liquid. So this is the point where these two, solid state and liquid state, they meet. That means at this point they have the same vapor pressure. Therefore this point corresponds to freezing point of this particular pure liquid. So let's take this to be TF naught, okay, and the vapor pressure corresponding to this freezing point will be equal to P naught, okay, P naught. Now whenever we move on to, now this is for pure solvent, now whenever we consider the solution which contains non-volatile solid, then from our discussions, from our previous discussions, as well as whatever I have written over here, it is sure that their vapor pressure curve will be lower than that of what? Will be lower than that of the pure solvent. Now this is the vapor pressure curve for what? This point. Say this is D, and this is E. This point is E and this is D. Now this DE is the vapor pressure curve for solution, and this is in from D to this point till E. It is in which state? It is in liquid state. Okay, and from this C beyond C towards C, from E to C, then again it will be in solid state. So now for this solution which contains non-volatile solute, the vapor pressure of this liquid and the solid state is meeting at this point, this particular point. Then for the solution, this point E will be its what? The temperature corresponding to this point E will be its say freezing point of the solution. Okay, freezing point of the solution. Now this corresponding to this point, let's take this point to be P2. The pressure corresponding to this freezing point of the solution is taken as what? P2. Now we can, from this particular diagram, we can get what? Vapor depression in freezing point. So now to understand this, just look at this point. Now for this pure liquid, the freezing point was at this particular point, and it is taken as T0F, which is more than the freezing point of the solution. So this amount, after adding non-volatile solute, the temperature has decreased by this amount. That means there is this much decrease in temperature. Now this decrease in temperature can be calculated. Okay, so let's take it to be decrease in or depression in freezing point. Okay, depression in freezing point will be equal to T0F. This depression in freezing point is delta T F. Now this will be depression in freezing point will be TF, and this will be equal to T0F minus this point is TF. Okay, now if you take the corresponding values of this vapor pressure for this T0F and TF, then you can get that this will be equal to, this is your T0F. Now this corresponds to P0. This corresponds to P0 minus, and this particular point, which is you have TF, it corresponds to P2. Okay, so we get this from this particular graph. Now, in our previous discussion, we have discussed that this P0 minus P2, okay, is equal to P0 minus P2 is directly proportional to number of moles of the solid that is non-volatile solid. P0 minus P2 is directly proportional to N2. Therefore, we can write that this delta PF is directly proportional to N2. Okay, so we have arrived at this particular point where we have this delta PF is directly proportional to N2. Now, experimentally, what they found is this depression in freezing point. Experimentally, they have found that this depression in freezing point, that is delta TF, is directly proportional to what? molality. This small m, as we had discussed in our previous video also. This is molality. Molar. Okay? Don't get confused. It's not molar, it's molar. This m corresponds to this small m is what? Molar. So this is directly proportional to m. Therefore, we can write delta Tf will be equal to some constant. So let's take it as Kf into m. Okay? Now this Kf is molar depression constant. This particular constant is what? This is molar depression constant, or it is also called as what? It is also called as cryoscopic constant. So you have to remember this. This Kf is what? Molar depression constant. Now we have discussed about the expression for molality. Molality of a solution will be equal to weight of solid divided by molecular mass or molar mass of solid into 1000 divided by weight of solvent. So weight of solvent. So this M can be written as weight of solid. For solid, it's always written as 2. Okay, please remember W2 divided by molecular mass M2 into 1000 divided by weight of the solvent. Now, weight for solvent is always written as 1. Please don't get confused with regard to 1 and 2. So if we substitute this value over here, then we get the expression. So we get the expression as delta Tf equals to Kf in place of m is being substituted with this value, then we will be getting W2 by M2 into 1000 divided by W1. So from this expression, mostly you will be asked a numerical based on this expression. Okay? So this is depression in freezing point. Now this is, as I told you, molar elevation, not elevation, this is depression. Molar depression constant. W2 is the weight of the solid. M2 is the molar mass of solid. And W1 is the weight of the solid. Now, mostly from this equation, you will be asked to calculate the molecular mass of the solid. So this expression is very, very important. Okay, please practice the numericals based on this expression. Now, as you already know it, in your book you have some solved numericals based on this expression, as well as there are some unsolved numericals. You have the IST questions at the back of your exercises are there at the back of at the end of this particular chapter. Please practice them properly. Thank you.